All right, welcome everybody. Let's get started with our 9th lecture on image processing and retrieval and analysis. And here is our menu for today. I thought it is a good idea to spend a rather extended period of time on recalling and remembering what we have done in the last 3 lectures. And once we have reminded ourselves of what the Fourier transform of a single real valued, of a function of a single real valued variable is, we can then ever so briefly extend these ideas to multivariate functions. We will then briefly discuss the idea of the discrete Fourier transform, and then move on to the next big thing, that is an application of the Fourier transform. And of course, in the project, we have already seen why maybe we are doing all of this. So we'll have a look into the notion of Fourier spectra and the idea of filtering, and an instance where this idea of filtering may be useful, namely the problem of denoising noisy signals. I'll summarize what we have been doing today, and then also briefly talk about an exercise you might be doing. Okay, we have been studying the abstract idea of something that is called the Fourier transform. And we actually began our study of the Fourier transform by means of looking at something that is called Fourier series. There's a difference there, and it will become apparent soon. Our starting point was that we were interested in periodic functions of a single variable, f of x, and without loss of generality, we assumed that period to be 1. This is something we may do. And we then agreed that a fairly general form of such kind of functions could be to express them in terms of a linear combination. Here's a sum where the index of summation k ranges from 1 up to n. And then there is a coefficient alpha k, and then there is a periodic function psi, which again depends on a couple of parameters. Once again, it depends on the index of summation k, and then an angle phi k. And in this representation, our model, this is our model of periodic functions of period 1. All the parameters that occur in this equation, that is the a naught, this constant in front of the sum, a naught, as well as all the alpha k, all the phi k, and then all the frequencies, nu k, which is a shorthand for 2 pi times k. All these numbers, and there are a lot of them because we have at least n of those here, are real numbers. All of them are real numbers, and if you start your favorite plotting program and have it plot functions like that, they will look periodic, and you can do this. Everything is straightforward, real numbers, easy to write down in terms of a computer program. However, we then moved on to expressing this model of our understanding of what it means to be a periodic function of period 1. We expressed it in a different form. All we have been doing here, to go from here to here, was algebraic manipulations. Lots of rearranging of equations and introduction of new variables, ck here. This ck now sort of includes a couple of these parameters over here. And in particular, instead of expressing this function as a linear combination of sine waves, we now express it as a linear combination over complex exponentials. These are complex functions. We have, again, 2n of them, 2n plus 1. Because now, since we have written it in this complex valued form, we actually have to sum from minus n to n. But there's a straightforward transition from here to here. We have a sum ranging from minus n to n. This is a complex number. And this is a function that depends on a real variable, but it produces a complex value. Because there is e to the I something that is a complex valued function. And the take-home message is that we can express this in this form, but we have to be careful because the summation has taken a new form. And whereas the parameters were real numbers in this model, they are now complex valued numbers. And another way of writing this ck is to pretend that it was actually a function of k, and I call it f hat of k. And for this f hat of k, we found that we can express it in terms of this integral over one period. We are interested in periodic functions of period 1. Integral from 0 to 1, and then the function we are given, f of x, times the complex exponential e to the minus I 2 pi kx, all of this dx. And the value of this function f hat at k, so basically this expression, is called the kth Fourier coefficient. And we then briefly, not really rigorously, but briefly pondered the question, is the model we have been considering up until that point general enough to express any possible periodic function we can think of? And we found, well, yeah, sort of from intuitive considerations, now that may not be the case. We would have to change our model ever so slightly. And well, the slight notational change is to change the index of summation now ranging from minus infinity to infinity. Like in terms of writing it down, that is not much. But in terms of the mathematics that happens here, this is tremendous. Right, we have now an infinite series. An infinite series. And this is actually called the Fourier series of f of x. Right? And we note that for the assumption we have made, or our starting point, the starting point of our discussion, that we want to consider periodic functions, and again without loss of generality of period 1, that these functions can be represented in terms of a series that is a summation over infinitely many indices. Now, why would we require it to range from this sum to range from minus infinity to infinity? We had a look at a couple of examples that sort of helped us to justify that this was again not really rigorously. I told you that if we're dealing with sharp edges, these periodic functions that are not really smooth, this is supposed to be a periodic function, so like this trapezoid form continues all the way to minus infinity and all the way to plus infinity, but we are just looking at one period here. This is not a smooth function. Right? There are, it's continuous, so there is no jumps in there, but there are certain points where this function does not have a derivative, which is to say it is not really smooth, which is to say it contains sharp edges. Well, they are not so sharp here. We can see that actually if we were to represent this function in terms of a Fourier series, where we start at minus 1 and go to 1, so minus 1, 0, 1, we would get this orange approximation here, which is it's not entirely wrong, right? If we agree that the basic thing we need to know about this blue function is that it rises, reaches a peak, which is fairly extended, and then declines again. This is expressed in this orange function already. It rises, reaches a peak, and then goes down again, but it's rather far away from the blue function we want to represent. Now then, if we increase the number of terms in our series representation of this blue function from 3 to 7, so we sum from -3, -2, -1, 0, 1, 2, 3, we find that the resulting orange curve, this orange curve once again is this summation over these complex valued coefficients times complex valued functions, gives a surprisingly much better representation of this blue function. And if we further increase the range of summation, now from -5 to 5, it becomes even better. And if we go to a summation from -9 to 9, this looks shockingly close to this blue function already. And again, it's a miracle. I know why it happens, but still, each time I see it, I'm amazed. Now, this is an example of a function that has sharp parts, edges, let's call them. We can sharpen them. For instance, here is another function. The blue one is now called g of x. Again, we try to approximate it in terms of these finite Fourier series. And we find that whereas in the previous example we had a fairly close representation for 11 terms already, when n was equal to 5, here it's not as close. We observe some over and undershooting, in particular in the vicinity of these edges. Nevertheless, if we increase the number of terms to 19, then again we are fairly close already to the function we want to approximate. However, most sort of the steepest possible periodic function we can think of are these rectangle functions. Those are functions that, for instance, have a value of 0 for a certain interval and then all of a sudden jump to 1, remain at 1, and then jump back to 0. These are the steepest edges we can think of. And very careful, I probably should not actually draw these things because there is a discontinuity from here to here. Right? This is just for visualization, it's not really there. And here we see that, well, it gets worse. Whereas we had fairly good results for these cases in the two previous examples, we now find that for this rectangle function in this example, even if we go to 19 terms in this series approximation, we are really dealing with severe over and undershooting, in particular, once again, in the vicinity of those edges. And given these examples, we say, well, apparently we have to sum a lot of these complex valued exponentials, and the most we can sum are infinitely many, so let's go for infinity without proof. All right? And then we thought about the question why I was so happy with this result, where we established a couple of lectures ago that the Fourier coefficient may be written as such an integral, and it's of course madness. Why should we be happy with such complex integrals? Does not really look as if we would have gained something here, just another very difficult mathematical function. Why should this be a great result? Well, it turned out that this integral is indeed an inner product between two vectors. And we spent some time on arguing that functions are vectors, between two functions, or vectors, in the vector space of L2 functions defined over an interval. Right? And in particular, our interval ranges from 0 to 1. And yeah, this is an integral, bounded integral. It has a function times the complex conjugate of another function, and we integrate over all the x, and this is exactly what defines these inner products. Right? So this is why I was so happy about our realization that the Fourier coefficient is given by this integral, because this integral is an inner product between two functions. And we know from our classes on linear algebra and the geometry of linear algebra that the inner product between two, say, vectors in some vector space over the real numbers, like those vector spaces we are familiar with, these inner products are basically projections of one vector onto the other. Right? So what we have here is that the Fourier coefficient is a projection of the function f of x onto these complex exponentials. And again, there are a lot of them. This is for one k, and this k appears here. So for every k, there is such a complex exponential. So now then, what does that mean? That it is an inner product? Well, we basically plugged our newfound knowledge back into the Fourier series expansion of the functions we are interested in. So that is to say that instead of f hat of k, we sum where k ranges from minus infinity to infinity, and then we have this inner product here, and then this number inner product always produces a scalar. This scalar is then multiplied again by such a complex exponential. Well, this may already look familiar. We try to make it even more familiar by looking at the inner product between two such functions, that appear in this expression. And we found that if we're computing the inner product of a function e to the I 2 pi k x and another function e to the I 2 pi m x, then this inner product for periods of 1 evaluates to delta km, which is a fancy way of saying that this assumes a value of 1 if k equals m, so if these are the same numbers, but it will always be 0 if these numbers are different. And this is, of course, a property we are familiar with from our discussion, say, of basis systems or coordinate frames, where we say that either in fancy terms a basis spans a space, or we are given a coordinate system which requires us to define a set of axes, which we can do in terms of unit vectors, and any two such unit vectors, if we're talking about Cartesian systems, are orthogonal and of length 1, and this is exactly what this means. If we compute the inner product between two vectors that are orthogonal and of length 1, then it will either evaluate to 0 if the two vectors are different, or it will evaluate to 1 if they are the same. And that led us to the deduction that the set of these functions, and this is a large set, this is a really large set, because for every k we have such a function, and we have really many k's here. The set of these functions constitutes a basis for the vector space of L2 functions over the interval from 0 to 1. Right? And we discussed, once again, we briefly discussed it, that we can think of functions as vectors, and even though we are not used to thinking of functions as vectors, we may, and if we do that, then we see that we have uncovered something here that is actually familiar to us. Right? Usually these vectors we are talking about are, I don't know, tuples of real values, but we can, if we make this conceptual leap, understand all of what is going on here as the Fourier series represents the function in terms of a set of basis functions. And this is a straightforward extension of what we know. Here is an example. So this Fourier series on the previous slide, number 1 here, is a Hilbert space generalization of the familiar representations of vectors. And for instance, let us consider a two-dimensional vector x in the vector space R squared. That is to say, if we look at vectors x that consist of two elements, two components, x1 and x2, whenever we write a vector like this, we implicitly, and this is something your brain may have internalized already, so you do never ever actually think of what you're doing when you write x is the vector of x1 and x2. What you are really doing is to say that this vector x is a number x1 times a basis vector e1 plus a number x2 times a basis vector e2. And these numbers x1 and x2 are actually the inner product of the vector x and the first basis vector in this example, and the inner product of the vector x and the second basis vector. And so another way of writing this is to say we have something where I should have called it k. So this is not the complex unit here. We sum over, well, let's call it k, ranging from 1 up to 2, and then we have an inner product times a basis vector. And once again, this we all know, right? But this is exactly the same as that. The difference here is this nasty thing. This nasty thing. So I said it last time, I say it again. Whenever you see this infinity sign in any equation, then you know things are a bit more involved than they usually are. And because of the occurrence of the infinity sign in the Fourier series, I actually say that this is a Hilbert space generalization of those familiar cases. Hilbert spaces are vector spaces. They are in a certain sense very much like those vector spaces we are all familiar with, but in a certain other sense they are really special. And what makes them special is that they are of infinite dimension. And again, whenever we are talking about infinity, things are a bit more involved. But we can nevertheless work with Hilbert spaces, and we will do so next week. That was our first major result. Let me go back here. The first major result was that if we are dealing with periodic functions, we can express them in terms of a Fourier series, which is to say a summation over infinitely many terms involving Fourier coefficients, which we know are inner products now, and complex valued exponentials. That was the first major result. Then the natural question to ask is, of course, now what about functions that are non-periodic? And so far, all of our discussion was focused on the case of periodic functions. One way of transiting from this special case to this, say, general case of non-periodic functions is to pretend that a function that is not periodic is the limiting case of a periodic function. And I argued that instead of periods 1, we may consider general periods, let's call them t, and then we let this t become very large, which is to say there's no period anymore. And in that sense, aperiodic functions are just limiting cases of periodic ones. If we were to succeed with this idea, we would first of all generalize the notion of the Fourier coefficient, this f hat of k function. This will then become the Fourier transform, and we would also generalize this idea of the Fourier series, that is this summation over infinitely many terms. And instead of Fourier series, like once we carry out this generalization, it's not called Fourier series anymore, but inverse Fourier transform. Okay, So here is what we looked into last time. If we assume a period t, we can still, I mean, there's, you know, I said without loss of generality, let's consider period 1. We may consider periods of t. That does not make much of a difference for the Fourier series representation of a periodic function. We still have this summation where k ranges from -infinity to infinity. Then there is still this Fourier coefficient. The thing that changes is the complex exponential. It now becomes e to the I 2 pi k over t times x. That's all that is all there is if we change the period from 1 to t. And we can walk through all what we have been doing up to now again and would find that the Fourier coefficient then can, or let's say should be written as 1 over t, and now an integral where we integrate from 0 to t, f of x, and then times the complex conjugate of this complex exponential, and again integrate with respect to x. And I encourage you to verify at home that as long as f of x is a periodic function, it doesn't make a difference if we integrate from 0 to t or from minus t over 2 to t over 2. Both these things are integrals over one period. Doesn't make a difference. The thing we should probably worry about is this factor of 1 over t in front of the new Fourier coefficient. Where does it come from? Well, it's a technicality. In particular, we observe that if we are now dealing with these complex exponentials and compute the inner product of one such complex exponential, again where we have this division by t in the exponent, with itself. So we compute the inner product of e to the I 2 pi k over t times x with itself. We plug this into the definition of the inner product of functions like that. We find that this integral evaluates to t. And this is something we would not want if we are talking about basis functions. We want them to sort of have an inner product of 1 if they are the same, and again if they are not the same this will be 0, but if they are the same this is t now, and so therefore we plug 1 over t in front of this just to normalize this inner product. And then some magic happened. First of all, introducing the idea of the angular frequency is not really magic. This is straightforward. I said let us, instead of 2 pi k over t, let us call this omega. And that's actually, everybody does it. This is a physical quantity, and it is called the angular frequency. And so there's nothing special there. We may use this equation to rearrange the terms in order to obtain a expression for k, the k that appeared in all our equations so far. And again, this is also straightforward. Another thing we may do is we may want to or can derive this, say, function omega. It is a function of k. This k changes, right? So this actually, there are lots of omega. Probably should have anyway called it omega of k. I don't really care. We can derive this omega with respect to k. This is really straightforward. All we get is 2 pi over t. And then if we were to multiply the dk on both sides, we would get that dk is equal t over 2 pi times t omega. And then I said, well, for the setting we are dealing with here, let me go to here. The setting we are dealing with, the dk is actually 1. Well, think of it. K basically ranges over all the integers, right? Say minus infinity to plus infinity, and at some point we have k is 15, and the next summation is 16, and the difference between 16 and 15 is 1. So every step in k is actually 1. Every dk is 1. Yeah. This is not the mathematically most precise way of exposing this. I would have to be much more precise if this was a math class, but it isn't, so we can keep it at that. Right? This can be proven, like this can be proven very, very rigorously, but we'll leave it at that. Here's actually nothing special happens. I have just replaced the 2 pi k over t with omega, but no problem there. And again here, I have just replaced the k's with omega t over 2 pi. Again here, we would have to be more careful, but it is good enough for us. It's good enough for us. This is not entirely wrong. It's not entirely precise, but it's okay. Now we can multiply this by a1, and this 1 is the same as dk, and for dk we have found this beautiful expression here, so all of a sudden we have a d omega, and we have something here which, if we let this t become very large, actually becomes an integral. So from here, which we can understand intuitively, this summation over very many terms, if we let this t become very large, then this summation becomes an integral, and this is with respect to omega. And yeah, well, I have just plugged in the definition of the Fourier coefficient here, and this 2 pi came from this t over 2 pi, the t cancelled out with the Fourier 1 over t Fourier coefficient. So what we find is that we can, in the limit, express these functions as 1 over 2 pi times the integral from minus infinity to infinity, and then over another integral from minus infinity to infinity, f of x e to the minus I omega x dx. This integral has to be multiplied by e to the I omega x d omega, and to make it a bit more symmetric, we split this 1 over 2 pi into 2 factors, and this is what we get. And yeah, well, now we find that there is an integral 1 over 2 pi something e to the minus I omega x, and then there is an integral 1 over 2 pi integral something I to the omega x d omega. This looks very symmetric. This is indeed the kind of symmetry we appreciate when we are doing mathematics. And given this expression, we can now assign names to the constituent parts of this expression. And those names are the Fourier transform of f of x, and we call it capital F of omega, and it is this inner integral thing here, this one, this thing in the square brackets. This is called the Fourier transform. And the outer integral that involves this f of omega is called the inverse Fourier transform. This really, there's a beautiful symmetry going on here. Now, why have we done all this? Why would I walk you through all of this? This is because if you read textbooks on image processing, they start here. They say the Fourier transform of a function f of x is defined as so, and the inverse Fourier transform is defined as so, and they have a couple of properties. Let's first diss these books a bit. So they start here, and then they throw a couple of properties in front of you, and then they say, and we use this for the following purpose, blah, blah, blah. So what I'm criticizing here is the strange habit of certain books written for a computer scientist audience to hand you a hammer. This is a hammer. which you can use to hammer in like really nasty nails. So those books hand you a hammer, but they don't really teach you how to properly use the hammer. And that can be dangerous. If you have a tool and you don't really know how to use it, in the real world you may hurt yourself. And with respect to mathematical tools, you may not use them properly, which in science is the worst thing you can do. If you do something and you don't really understand what you're doing, I am sorry, this is the worst case scenario possible. Unfortunately, we have reached a point where this is more or less the norm. Why is that? Because we are all computer scientists and we all know how to search the internet for stuff. And we can download thousands of libraries that do things for us, and then we, I don't know, maybe not even read the manual and just run it and get some results and then claim that we have found something which may actually not be the case because we use those libraries in not the correct way. And this really, I'm ranting here right now. This really is happening, and you can read the scientific literature, and a huge percentage of what is being published, say, in the area of image processing and analysis these days is, excuse my French, bullshit. And the reason is that people are not properly educated. And this is why we have done all of that, right? I have handed you a hammer now and told you how I forged it, like where it comes from, what it does. In particular, what we know by now is that, yeah, okay, we have not made it precise for the Fourier transform yet, we will, that this is just a basis transformation. Right? We sort of take something, let's think of it as a vector, the function, which is represented with respect to a certain basis system, and if we do this here, we express the vector in another basis system. And we have seen that when we talked about simple affine transformations, right? And so this is a tool for changing our point of view. Changing our point of view on something that we're given, and we'll come back to images soon. This is all about images in the end. And now you know what it is. Not really precisely with respect to these integrals. I will make that much more precise next week. But you understand where this hammer comes from. And once again, going to university is about education and not about training. This is an example of education. Now that you have seen this, and this may still be very sort of abstract to you, but now that you have seen it, and if it ever reoccurs later on in life, you know maybe where to look it up again. And in particular, later on in life, you might find an occasion, in particular those of you who move on to become scientists, say, this is not a really good hammer. What are the drawbacks of this hammer? Can I probably improve the grip of this hammer to, you know, more confidently hammer something? So then what would I have to change? If you understand these things from first principle, you can confidently work with them and maybe even make changes to them. If you just download libraries from the web, do something, hit return, get some result, you cannot do that. Right? This is about education, and I have educated you about what these things really mean. They are basis transforms. Okay, and yeah, these two sentences just make that again, or summarize that again. We can think of the Fourier transform as analyzing or chopping a given function into its constituent parts what is it made of? A set of basis vectors, which in this context are, well, complex valued functions. And the inverse Fourier transform takes these parts and, you know, recreates the function of that. So as the Fourier transform analyzes f of x into parts, and the inverse Fourier transform synthesizes f of x from more elementary parts. And there are a couple of, okay, I say some noticeable properties. These things are really like one of the most powerful full hammers we have in mathematics, and has numerous interesting properties. For instance, if we were to compute the Fourier transform with respect to omega equals 0, the 0 frequency, then we have e to the I 0 times x, but e something raised to the power of 0 is always 1, so that goes away. So the Fourier transform of at frequency 0 is actually the integral over the function. Interesting. It is fairly straightforward to prove that if we compute, this is strange notation, but be with me, if we are given a shifted version of the function, right? So say, I don't know, some function, and then we move it by an offset a along the x-axis, this is what this means, and compute the Fourier transform of this, and we ask for the value of the Fourier transform of this at omega. This is how we have to read this, right? Then we find that this is the same as the Fourier transform of the function f not shifted, evaluated at omega, times a certain factor. You can verify that at home. You just have to plug in the corresponding integrals and then play around with these integrals, and this is what you find. If we are dealing with a scaled function, I know we have something and we sort of scale or shrink it by multiplying some factor a to the variable x, we compute the Fourier transform of this scaled function evaluated at omega. It is fairly easy to see that it is given as the Fourier transform of the original function f of x evaluated at omega over a and then scaled by 1 over the norm of a. And these are just, you know, just showing them so that you can appreciate that there might be situations where you have to deal with evaluating things like that, which may be very difficult. It depends on how these functions look like. And well, if we can master the Fourier transform, then we can probably again reduce these more difficult problems to simpler ones. Right? I'm just saying. So let's move on to new shores. What we have been discussing to this point was basically the idea of the Fourier transform of a variable function that depends on a single variable. We can generalize that, and I'll actually sort of do it like in the textbooks. But this is okay because, you know, this is a leap of faith that is more easily to take than to say, well, the Fourier transform is defined, like where does this come from? And now we know. And now we know, okay, so if it works with one variable, it might work with many variables. And indeed, if we are given functions like this, right, depending on n variables, we can compute corresponding Fourier transforms, which of course then will also depend on n variables. And yeah, there you have it. This is how they look like. And this is actually too general for our purposes. However, the libraries you are using in your projects, they can do that. Don't worry, they'll do it for you. The thing we are interested in is basically these two-dimensional functions, functions defined over two variables, an x and a y variable. For those, the Fourier transform, so if we're talking about the function f of x and y, boils down to this. We have 1 over 2 pi. So have a look here. There is this 2 pi raised to some n over over 2. In the case where n equals 2, this is actually minus 1, so 1 over 2 pi. And then this double integral f of x and y, and then the complex exponential is now also a function defined over 2 variables, x and y, and it is given as e to the minus I, and then mu x plus mu y, 2 more Greek letters here, mu and nu, and of course this is integration over x and y. This is the 2-dimensional Fourier transform, and again, beautiful symmetry. This is the inverse 2-dimensional Fourier transforms, 1 over 2 pi double integral. Now this 2D Fourier transform, and here we have the complex exponential without the minus sign, and we have to integrate this expression with respect to the variables mu and nu. That's all there is. This is all good and well, but now this is a course on image processing, and we spent some time on discussing the fact that digital images are discrete functions. And these things are continuous functions. This is supposed to be a continuous function, this is supposed to be a continuous function. Can we really use that? Not really, but it turns out that we can now again make our newfound knowledge sort of more less general. There is indeed something that is called the discrete Fourier transform, and well, we have not derived the discrete Fourier transform. Our train of thought was, let us understand where the Fourier transform comes from. We can now appreciate that, and then I will hope that you can simply accept the fact that we may do that for discrete functions as well. So this is again to say that now x and y are not continuous, but there is an x, at discrete points, and y is at discrete points. I'm expressing using these square brackets here. It's not quite as symmetric anymore. I don't actually at this point recall why not. We can of course make that symmetric by again introducing square roots, but it is not, and this may be because this is how it is realized in all the libraries, I would assume. Otherwise I don't see why it should be symmetric. Anyway, this is how the discrete 2D Fourier transform and its inverse are defined, and I don't bother with the one-dimensional one this because images are 2D. Yeah, so what we have here is we do assume that the image we are talking about has m columns and n rows, and so the pixel coordinates x and y can range from 0, 0 to m minus 1 and n minus 1 respectively. And we have a summation, no integration here. This is because it's discrete. Here is again the image in the Fourier transform. It appears here. And then we have this complex exponential, which is now given like so. So there's no omega, no mu, no nu. We have this 2 pi and then mx over capital M plus ny over n. These are all basically discrete frequencies. No continuum here anymore. Discrete frequencies. And then again, yeah, it's not as symmetric as Fourier transform, but basically the same. The only difference is now this and the switch in the sign. So this is how one can show how to compute Fourier transforms for discrete functions. Is there a problem here? Now these m and n are finite. There is no such thing in practice as an infinite image. It just does not exist. We don't have that. And instead of integrals, we have these sums again. And in particular, they are finite. Now, what would that mean? Given our discussion earlier, in particular our discussion about the periodic functions and their Fourier series. And then we discussed that, well, we go from series to transforms by means of considering periods that become very, very large. This is apparently not possible here. Right? So this is a violation of what we discussed in the last 20 minutes. And this is not a violation sort of we choose freely, but it's a violation that comes from the fact that in practice the things we are dealing with are discrete and finite. So, but nevertheless, this is more akin to those Fourier series than it is resembling these Fourier transforms. But nevertheless, it's called discrete transform. But as it is more resembling what we discussed when we discussed Fourier series, we can understand why this may work anyway. Now we have these finite sums, which we had at the very onset of our discussion when we talked about periodic functions and minus n to some n, whatever summation. And this is exactly the case we're dealing with here. So in order for these two definitions here, the discrete Fourier transform and its inverse, to make sense, in order to make sense, what we do when we compute this, and we don't do this explicitly, we implicitly assume that the image we are dealing with is actually periodic. And it's periodic of periods m and n. And this is what this means, but again, a picture says 1,000 words, so here we go. If I am giving this image, right, and want to compute the discrete Fourier transform, I can do this. I can pipe that image into the functions provided by the libraries, and then they happily compute something. But what they are actually computing is, and this is never made explicit, but the mathematics they use assumes that the image indeed looks like this. That is, this is the image we're given, but in all directions it is continued all to infinity, and it's actually periodic. Right? And this is really periodic. It's periodic in x direction with a certain period of, what was that, m, period m, right? And it is periodic in the y direction with period n. So you don't have to worry about that, because the software does it for you, and the software does not create these infinitely large images, but the mathematics the software applies implicitly assumes that whatever you pipe into the functions actually is this. Right? And that has certain implications. In particular, there are edges here in this function, which you would not think of as being there if you just look at one image. Right? But if you, once again, compute discrete Fourier transforms of digital images, you might find artifacts, let's say, which at first sight you cannot explain, but if you consider this, you know where these artifacts come from. Right? These equations only make sense if we were to assume that these are actually functions defined over an infinite range. But in practice, all we are given is a very finite function. However, implicitly, the mathematics assume this is continued to infinity in all directions. Okay, now, you have done that, of course, in the project already. How do we compute all of this, right? There is, and this is another miracle of mathematics, an extremely efficient way of computing this. And I am not discussing this because why, you know, we have now a hammer in our toolbox. We know where it comes from, and since we know where it comes from, we know how we may use it. But how this hammer was actually produced, that is not of interest to us, because I could now discuss this fast Fourier transform algorithm, and again, like lots of textbooks do that, but nobody in this room will ever implement the fast Fourier transform on their own, and rightfully so, because the danger of you introducing errors into that is much higher than using the really well-tested libraries that are out there for free. So if you want to compute Fourier transforms, you will typically do this with respect to discrete signals, because all the files on your hard drive are sort of discrete functions. That is, you'll have to apply the discrete Fourier transform, and this can be computed practically like in extremely efficient ways. We will not look into how this is being computed, but we will have a look at how efficient they are a bit later on. Okay, to wrap this up, I have to point out that there are numerous other hammers out there. There are many, many other transforms that are similar in spirit, and some of them are indeed very important in the area of image processing. Probably the most important one from a very practical point of view is the discrete cosine transform, because this one is actually at the heart of the JPEG compression algorithm. But all of these techniques are just basis transforms. And we have now seen that the Fourier transform is a basis transform in a very abstract vector space, granted, but it is just a way for us to change our point of view on something, right? I can look at the laptop from over here or from over here. Depending from where I look, I might be able to recognize something about the thing I am dealing with that I cannot recognize from my original point of view. All these transforms are just changes of viewpoints, and two of them, the Laplace transform and the Z transform, will come back later. And we can now easily do that. Easily, sorry, please excuse my use of that term. We can now do this at least because we have gone through one of these tools from the very onset on. Right? So when we will discuss these two things in 2 weeks from now, things may not be as shocking to you as they could have been. Okay, now, where or why do we need all this? And again, of course, you have done this first project already, so you have seen very interesting application of this. To familiarize ourselves with that, let us get a grip on the notion of the Fourier spectrum. And on the left-hand side here, I have plotted a very simple function. It's a periodic function of period 1. I have made sure 2 pi times 2 is like, you know, one rather slow sine wave, and then there is 2 pi times 8 rather high frequent sine wave. And I have superimposed the two and divided by 1 over 2, so that actually starts at 0 and goes to 0 in one period. So this is a periodic function. This is how it looks like in the space domain. Let's call x the space variable, because in images quite often you find functions over time here, time series, then it would be f of t, and the x would be t time, and then it's called the time domain. For us, images are not like, you know, we have an x and a y coordinate, gives us some plane, some spatial thing, we call it the space domain. This is how the function looks like in the space domain. And we can, of course, now compute the Fourier transform, right? F of omega, capital F of omega. However, that is a complex valued function. The omegas themselves, they are real numbers, but the value of f at omega is a complex number. It's very difficult to plot these complex numbers. Here, in this case, I could have actually done that. I have chosen not to. Instead, what I am plotting here is the norm of f of omega, which is a real number. I can plot that, no problem there. And I have plotted this norm of the Fourier transform with respect to the omegas. So where this is x for one period, here I'm plotting the Fourier transform over the omegas. And of course that would go from minus infinity to infinity. I've chosen some space here. Right? And this is how it looks like. So basically, what do we recognize there? 4 large candlesticks. And we note that one of these candlesticks is at 8, and the other one is at -8, which is interesting because there is an 8 here. And then we have a candlestick at 2 and another one at -2, which is interesting because of that 2. Well, it's actually not that interesting because given all our discussions so far, we now say this is a periodic function of period 1. And we can compute its Fourier coefficients, and this is what I plotted there. I'm talking about transforms now, but you know, it's actually not necessarily to use this more general expression, but let's talk about transforms. And this one is made out of 2 basic building blocks. And recall that instead of sine, we could also express that in terms of these e to the I something. And if we do it with the complex exponentials, we also have these negative frequencies. We discussed that briefly last time, or previous lecture before the last one. So yeah, that makes sense. We find that this space domain function in the frequency domain, omega as a frequency, has 2 major components, which look like 4 major components because of the complex exponentials, but you know, basically there's these 2 major components in there. And then there are these things. They shouldn't be there. If I would have done this with pen and paper, and I could have done this with pen and paper, right, because this is easy, they wouldn't be there. Right? I could have computed the closed form expression of the Fourier transform of this one, but I did not. What I have been doing is I wrote a Python program that basically computed this function between 0 and 1 at, I don't know, I really don't know, 200 points, whatever. Here. And this is, you know, it looks smooth, but of course it is not, because of the way of how I created this plot. This is actually lots of points and tiny line segments between these points. So what I actually did is, it looks continuous, and this suggests it is continuous, but on my computer, this is a certain array of a fixed length, and the values in this array are plotted here. It's a one-dimensional array. Now this array I then piped into the functions for fast Fourier transform. It's something discrete, right? And because it is discrete and not really continuous, when the Fourier transform function starts crunching this thing, it cannot recognize that this is not originally something continuous. It treats it as something discrete. And therefore it finds certain other contributions by certain other frequencies which theoretically are not there. So these tiny things here are practical artifacts that result from the fact that when I created these 2 plots, I did not do it with the pen and paper method and sit down and evaluate the corresponding integral. I just created a certain array, I don't know, typically I use 200 elements, whatever, filled it with numbers, and this array was then Fourier transformed, produced another array of length 200, now containing complex numbers, and I took the norm of these numbers and plotted them like so. So these things should not be there, and the reason why they are there is, again, an artifact due to my use of a digital computer to produce these plots. Nevertheless, given this caveat, what we can recognize from looking at this is called the Fourier spectrum on the right, that there apparently are 2 very dominant frequencies in this function. And this is indeed the case. Because this is a superposition of two sine waves, one with frequency 2, one with frequency 8. And we have these spikes at 2 and 8. So it works. Then images, right? This is what we are interested in, not these 1D things. We can, of course, do the same for images. And indeed, this is what I have done here. When I created the image on the left, this is actually 256 pixels times 256 pixels, but I pretend that this is period 1. And so therefore this is a function of frequency 5, apparently, function with a certain frequency along the y direction. Frequency is 5. And actually what I really did here is just, I computed something like that. This was actually not there. It's just a sine wave. I took an array and I filled it with values such that along the y direction we have a certain sine wave. And now we're looking on top of the sine wave. So there are hills and valleys, hills and valleys, hills and valleys. This is a sine. This is really just a sine wave. Yeah, and I said the frequency is 5. So first of all, this, this is rather constant along the x, no periodicity there. But there is this periodicity along the y-axis. And if we compute the Fourier transform of this and plot the spectrum, that is the absolute values, it's now also a two-dimensional object. And we have this nu and the mu. Should don't have it here anyway. We see, yeah, indeed. So there is something at frequency 5 along the y direction. What is this? At 0 here, 0, 0. Why is that there? Where? Pardon?
It's the integral of the image.
Exactly. Let me ever so briefly do this. Look here. Right? We said, to be very general, let's put an offset constant in front of it. And that is actually, where was that? This is indeed this, sort of. This is the Fourier transform at 0. And why is that not 0 in this case? The reason is that if you compute sine waves such as this, and I just actually used 1, here it's 2, but note that of course, since it is sine something, it is always something between -1 and 1. There's no amplitude in front here actually, right? It's always something between -1 and 1. A digital image contains pixel values between 0 and 255. 255 is white and 0 is black. So actually when I created this image, I had to scale this function that assumes y values between -1 and 1, the sine wave, which I computed here. I had to transform it so that the -1 becomes 0 and the 1 becomes 255, so that I can plot it or create it as an image. But that means that what was the 0 value in the original sine wave is now 128, because this is exactly half length from 0 to 255. Right? So the average gray value of this image is 128. Is not 0. But this is because I have computed a sine wave and I wanted to illustrate it as a digital image. In digital images, the smallest gray value we can have is 0 and the largest one is 255. And so for this periodic thing, the average is 128. That is to say that at a 0 frequency, there is something here. This basically represents the fact that the average value here is not 0. And so therefore, in practice, if you're given these images, you will always have something at 0. And this will always be a very large value, because this is the integral over the whole image. If you compute that for values between 0 and 255 and large, that is usually a large thing. It is not present here. There is nothing at 0 here. Because here I would not have to worry about how to represent that. But if I would have moved this up, then there would have been a spike at 0 as well. So in practice, this thing will always be there. Will always be there. But apart from that, we recognize there are just, you know, 2 other peaks. Do you see them? Can you see them from the back? These 2 dots here? Okay. Now then, how would the frequency spectrum look like? Oh, one more thing. This is 256 pixels, 256 pixels. The corresponding Fourier transform, if we were to save it as an image, would also be of dimensions 256, 256. This is because of the summation in the discrete Fourier transform. However, then these things would have been tiny, tiny dots. And so therefore, just to make it more visible, I'm not showing you the whole Fourier transform here, but just sort of a certain thing I cropped from about the center. So this goes from -32 to 32. It would have been much larger, but then these things would have not been visible at all. Right. How would this look like if it was rotated by 90 degrees?
Just rotated by.
Now let's verify that. Oh yeah. But we can easily appreciate that. Right now, this image is periodic along the x direction, and that is to say, it's again period 5, so we have these 2 peaks at period 5, but now along the x direction. Let's see, what if we have something like this? Again, it makes sense if you think of it. Now there is a period in this image along a certain angle, and I don't know, 30 degrees, I don't know. And we find that these 2 peaks that indicate the major frequencies are now angled in this representation. So yeah, this all makes sense. Then let's have a look at this one again. So we have seen this already. This is with period 5. How would it look like if I increase or decrease the period? Like so. This is period 3. Let me have a look at the right. Period 3. You see what I'm after here? So here we have, this is not as high frequent. So these 2 peaks move closer to 0. It's actually period 3 now. And here it's more high frequency. They are further spread out. So we recognize already that if something is rather narrow here, it is rather broad here. And if something is rather broad here, it is rather narrow here. Once again, I have plotted these things such that the 0, 0 point is in the center. This is how you usually visualize that. And so therefore, these low frequencies are things that are close to the center. And the high frequencies are things that are farther apart, or farther away from the center. Okay, here is, to wrap this all up, a superposition of 2 sine waves. And we now, I don't know if you can, they're very, very dark already, 5 dots surrounding this central frequency 0 peak. So, because this is now a sine wave composed of 2 elementary sine waves. We see 1, 2, 3, 4 additional dots here. So all these practical experiments sort of verify the theory we have been developing. Now, but of course in practice, we want to look at more interesting images, not necessarily just these sine waves. And here is a natural image, and there is its Fourier spectrum. And again, we recognize a very bright peak. Actually, here I had to take the logarithm, because if I would not have done this, then there would have been one white dot here and everything else would have been black. In the previous images, because they were just sine waves, I did not have to take the log. Here I have to in order for it to be visible at all. So this is how the logarithm of the spectrum looks like. Apparently there are a lot of low frequencies, that is, this image here is composed of a lot of elementary functions of rather low frequency, but there are also things here of rather high frequency. In all, this is another view on this. This is in the space domain, and this is an artifact because of the absolute value here in the log, but this is a frequency domain representation of the image. Okay? And now, what can we do with these kind of things? Let me ever so briefly, because this is really straightforward, introduce the idea of a low-pass filter. Notice that this is now the frequency axis, omegas here, not space domain, frequency domain. And I am defining a function, let's call it GL of omega, that has the property that is 0 to the left of some minus omega L, some constant. Then it jumps to 1, and then it jumps back to 0 again for everything that is greater than omega L. So this is a rectangle function. And I'm just sort of plotting it in the 1D case, but of course we can also define something like that over 2 variables, right? Then it would probably be like if we look at this in 2 dimensions, then it would be some cylinder surrounding the 0, 0 coordinate. If we would look at this in terms of an image, it would be some disk, and everything else would be 0. Like we can generalize that mentally to 2D, right? Can we? Because actually here it is. So if we apply these low-pass filters, what we do is we are given a function, an image, compute its Fourier transform, and then multiply this with the 2D version of the function we just saw. And everything outside of this disk, which we define in terms of this so-called cut-off frequency, omega L, if we multiply this with the Fourier transformed image, then everything here will be multiplied with 0, goes away. Everything inside this radius, the cutoff frequency, will be multiplied by 1, remains, and this is what we see. Everything out here was multiplied by 0, is gone. It's just a visualization, it's black now. Everything inside this disk is still there. And it is called a low-pass filter because we just ever so briefly established that the low frequencies are centered around here, and these are the more high-frequent parts of the image. And low-pass means everything that is low is let to pass, everything that is high is hold back, suppressed, set to 0. Right? This is a way of removing high frequencies. We just let the low ones pass. And then, of course, we might be tempted to compute the inverse Fourier transform of that, and this is what we get. Right. If we compute the inverse Fourier transform of this low-pass filtered representation in the frequency domain, we get another image in the space domain, and it is really blurred now, and really wavy. And this is because by setting all of these high frequencies to 0, we have removed the edges. We have removed the sharp parts of the signal. We discussed that earlier today. Right? The sharp edges require high frequencies. If we remove the high frequencies, those edges are gone if we go back to the space domain. We may, of course, sort of look at the inverse idea. Instead of a low-pass filter, have a high-pass filter. That is, there's another cutoff frequency. Everything left of that is 1. Then it jumps to 0, remains there until it hits the cutoff frequency again, and then goes back to 1. If we were to apply such a filter, to the frequency representation of the image. And beware, right? If we do this, we don't apply this to these images. This is the log of the norm of the Fourier transform. If you do this, you don't apply to the log of the Fourier transform. You apply to the Fourier transform, right? This is just for visualization. This is just for visualization. But if we do it, then what will happen is this. Everything inside this disk defined by that filter function is set to 0. Everything outside remains. What happens if we transfer it back? It will have suppressed everything that is not an edge. Oh yeah, it works. Right? And there is something I have to point out, but we cannot see it here. We can probably see it here. Do you see that there's like something here that is very bright? There's also something very bright here, but because the background is white, we can't see the white stuff here. Why would there be an edge at the borders of the image? Because?
It's coming from the heuristic used in the library.
It comes from the fact that this only works for periodic functions, right? And if we go back to this, like this is what really happens. Right? This is what the mathematic does. It computes the Fourier transform of this. And there are edges here. And so therefore, if you apply that, you use your computer to create these things, you may get stuff that is not intuitive to you. Or you would say, well, that doesn't make sense. But it does. It does. Right? And this comes from the fact that these are discrete objects which we can very efficiently manipulate using these discrete Fourier transforms. But then we have these things which are, there's another very bright stuff over here. They are there. We don't really see them on the white background here, but they are there. And don't be alarmed. It actually makes sense that they are there. Okay. Yeah. I guess this is the one you have already used in the projects. This is called a bandpass filter. This is because it suppresses everything outside a certain frequency band. Again, we define, now we have to have two cutoff frequencies, a low, and let's a low-high cutoff frequency and a high cutoff frequency, and of course, like for the negative side of the spectrum as well. Everything outside this frequency band is set to 0, and then for the negative part of the spectrum is again everything outside the corresponding negative frequency band is set to 0. So we may apply that. You have done that. Here's the image, a visualization of its spectral representation, a visualization of what happens if we apply a bandpass filter, and here is the outcome if we transform it back. Yeah. And this is something I've got some solutions already, but most of you should have found that. Okay, this is, you know, why? Let's think of it. Why would people worry about these kind of filter operations? And in particular, let's have a look at the effect of noise. Here's an image. Here is a noisy version of that image. Here is a visualization of the Fourier transform of that image. And here is a visualization of the Fourier transform of that image. What has happened? Well, this one is noisy. This is called salt and pepper noise. I have randomly turned certain pixels into white and certain other pixels into black. And I guess it's just 3% of the pixels. But look, just 3% of the pixels are distorted now. Quite a lot. What has happened? Like from here to here, we see what's the difference between this one and that one? Exactly. Exactly. This one is very dark in the areas where there are supposed to be high frequencies. Which is to say, if it is dark here, because it's the visualization of the length of the candlesticks, right? It's to say that there are hardly any high frequencies in here. There are, we saw that when we computed the edges, right? But it's rather dark here. But in the noisy version, it produces a Fourier transform. This is much brighter than over there. Which is to say, in this image, apparently to create this, this can be analyzed into constituent parts that are more indicative of high frequencies. And this is exactly what noise does, this kind of noise. Because where there was no real edge here, there now all of a sudden are these jumps in the signal. High, steep jumps, edges, right? High frequencies. And we see that there are, the contribution of higher frequencies is much higher here than there because this is much brighter. Again, this is just a visualization, all right? But already there we can see that. Well then, we may compute the Fourier transform of this, apply a low-pass filter, and we get that. At least the salt and pepper stuff is gone, all right? It's not black and white anymore. So in a certain sense, we could argue the noise is gone. It is, of course, not. Right? This is. If you I don't know, would be a Photoshop programmer and provide the users with image enhancement methods that produce that, nobody would buy Photoshop. It's like that, right? But we are getting there, right? What we see here is that it appears to be possible, and from what we have learned so far, rather clumsily, but it appears to be possible to remove noise in images, okay? And one way of doing that is by considering Fourier transforms and suppress certain frequencies. Yeah, and if you use a low-pass filter, you get that. Of course, probably consider a larger band, whatever it is, those are now parameters and people have to play with the parameters to get a good effect. I probably should have used different parameters here to make it not as horrible, but you see the general idea. You see the general idea. We are given something we are not really happy with. We transform it, we change our point of view. Now in this different viewpoint, we see something that is not desirable. We remove it and we get that. And next time we will learn more about the theory behind that. And once we can comfortably handle that hammer, we will extend it to better methods of getting rid of that noise. But for today, this should be all. We have now learned, or at least seen, the idea of the Fourier transform, in particular with respect to functions of one variable. We have seen where the Fourier transform and its inverse come from and what they are. Right? I did not really derive that, but I basically claimed that these things can be generalized to higher dimensions. And I also did not really derive that, but basically claimed that we can degeneralize that again with respect to discrete functions. But both these things could be made, again, very rigorous, but why should we? This is, this is easy to accept. Like once you have accepted that, then everything else is rather sort of easy to accept. And now that we have met this idea of the discrete Fourier transform, something we can very efficiently do with discrete images, with digital images that are discrete functions, we could then think about the ideas behind low, high, and band-pass filtering. Of course, this also applies to continuous functions, right? And the low-pass filter, high-pass filter, I showed you the word continuous functions. But if it works for continuous, it can also be applied to discrete Fourier transformed images. And this is what we had a look into. So there you go, that works. In particular, we will not ever in this course worry how to compute this. There is software that does that for you. It's extremely very high sophisticated software, and there's hardly any further improvement possible, so nobody will ever have to implement Fourier transform on that basic level. There is software that does that, the fast Fourier transform, very reliable, very robust, very fast. We'll not worry about it. If you are interested in how this is done, basically most of the books on signal processing contain a chapter on the fast Fourier transform. It's a very intricate, very sophisticated algorithm. It's probably one of the most important contributions of computer science to the human knowledge of humankind. It's been voted one of the top 10 most important algorithms of the 20th century. So the fast Fourier transform is really is a miracle. We are not going to study it. And for those of you who are not afraid of integrals, I want you to show me this, that the two-dimensional Fourier transform is a separable operation. Now this is the first time the keyword separable operation occurs throughout this lecture, and from now on it's a new friend of ours, separable operations. This is the first instance of such a separable operation, and this is basically already solved on this slide, but maybe there is one step in between here. If you could insert that one. What I want you to show is that this double integral can be computed sort of either like that, or you may first compute this integral and then compute the other. That's already what separable means. We'll come back to that later. The only problem here is to insert one more line between here and here. Right? This is a great opportunity for you to play with these kind of integral equations. There's not anything to be computed here, it's just algebraic manipulations. Go for it. See that this is indeed true. All right, that is all I have for today. Are there any questions? Great. We will meet again this afternoon for the projects, right? It's at 1:30 in this room, I guess. All right, see you then.